Hello everyone, I welcome you all to the lecture 12 of this course. In this lecture, we are going to continue our discussion on the scrapers. So in the previous lecture, we have discussed about the operation of the scraper, types of the scraper, and we have also discussed about what are all the components of the production cycle of the scraper and the pusher, and how to estimate the cycle time of the scraper and the pusher. So in this lecture, we are going to discuss, or we are going to work out some problems on the estimation of the productivity of the scraper, and we will also work out some problems on balancing the number of scrapers and the pushers, which are the interdependent machines. So now let us work out the first problem on productivity estimation of the scraper. So a scraper with the assistance of the pusher is moving the dry earth soil having unit weight of 1660 kg per bank meter cube. So you can see that this is a conventional pusher loaded scraper. Here we are moving the material which is dry earth soil. Its unit weight is given 1660 kg per bank meter cube. So the volume is given in volumetric measure is in bank state, so that you have to clearly note it, and the swell factor is given as 0.8. So with the help of the swell factor, you can do the conversions, like from loose volume you can convert it into bank volume or vice versa. And you should know that the swell factor will increase by 10% due to pushing. Why is it? Particularly for the push loaded scrapers. Okay, for push loaded the scrapers, your swell factor increases by 10% due to pushing. So basically, you know that when the pusher is pushing the scraper, it offers more additional pressure, okay, to push more material into the bowl. Okay, so because of that additional pressure, what is happening? More and more material gets compacted inside the scraper bowl. Okay, so due to the compaction of the material inside the bowl, you can see that the unit weight of the material inside the bowl will increase. So that results in increase of your swell factor. Okay, so hope you remember what is swell factor. We have defined what is swell factor in the earlier lecture. It is a ratio of loose dry unit weight of the material by bank dry unit weight of the material. So particularly for the push loaded scrapers, your swell factor, the unit weight, will increase by 10% because of the additional pressure which we receive from the pusher to the material inside the bowl. Okay, so the material gets more compacted inside the bowl. Okay, and because of that, the swell factor will increase by 10%. So this we have to always remember. So even though the value is not given in the question, you should know that for push loaded scrapers, by default swell factor will increase by 10%. Now assume the rolling resistance of 50 kg per ton. For this particular haul route, the rolling resistance is 50 kg per ton. So if you want to convert it into equivalent gradient, you know that for 1% of gradient equal to 10 kg per ton. So this is a conversion factor which we discussed earlier, and this is valid for slopes less than 10%. For slopes less than 10%, we can use this. So 50 kg per ton, it's going to be 5%. Okay. Heaped capacity of the scraper is given as 23.7 meter cube. Okay. The expected load will be 95% of the heaped capacity. So that means, as we discussed earlier, we are not going to load the scraper to its fullest capacity. If we load it to the fullest capacity, it will result in, because of law of diminishing returns which we discussed earlier, it will result in decrease in loading rate after a particular time. Okay, so that is why your loading time will increase a lot. So the optimum loading time we have to follow for loading, which we can derive from the equipment manufacturer. Okay, so here the expected load capacity is given to be 95% of heap capacity. That means we are going to load the scraper only to 95% of the heaped capacity. We are not going to load it to the fullest. And the corresponding average loading time is 0.8 minute. The empty weight of the scraper is given in kg. The maximum rated load it can carry is 34,019.42 kg. That means this is the safe operating weight. safe operating weight of the machine. For every machine, the safe operating weight is given by the manufacturer. We are not supposed to load the machine beyond its safe operating weight. So that will affect the structural frame of the machine. It will abuse the machine if you are going to load it beyond the safe operating weight. It will affect the safety of the machine. So we have to check whether your load of material within your bowl is going to be within this safe operating weight. Okay, that's a very important check we have to do, because the material density will vary from type to type. So we have to carefully check for the given material what is the material weight. So whether it is within the safe operating weight, we have to check it. The efficiency factor is given as 50 minutes per hour, the job efficiency. So your machine is working for 50 minutes in an hour. And the time data for various activities are provided in the table, which it's in the upcoming slide. Yeah. So we can see it here. The average loading time, okay, is given by the manufacturer as 0.8 minute. Hope you remember, it is given as 0.8 minute. Average dumping time, okay, you can get it from the manufacturer. It's available in the literature also. So I have taken it from the literature. So for 19.11 meter cube to 26 meter cube capacity scraper, the value of dump time is given as 0.37 minute. As I told you, your dump time is going to depend upon your capacity of your scraper, as well as it will depend upon your site constraints, the congestion at your site, and also it depends upon the type of material it is going to handle. So you can take it from the manufacturer, the value, or from any literature. The turn time fill, the average value is given as 0.21 minute, and in turning time in the cut area is given as 0.3 minute. So in the cut area it is slightly higher when compared to fill area. We have discussed the reason earlier. So these are the fixed time values, okay, which are provided to us in the literature or from the equipment handbook. The other input data given is about the path, okay, about the haul route, about the haul distance and the resistance encountered in the haul route. So you can see this is a pictorial representation of the haul route. You have the cutting area, you have the fill area, this is your haul route. So you can see that for the first initial 500 meter, okay, 500 meter, it is upslope. You have a gradient of plus 5%. Then you have the 300 meter, you have a gradient of plus 3%. Then towards the end, you have a distance of 400 meter with a downslope of minus 3%. So since different sections in your haul route have different resistances, okay, particularly the gradients, so we have to do the estimation section wise or segment wise. So that is the reason we have split the haul route into different sections. So another important thing you have to note it here is the first 500 meter I have demarcated 60 meters separately. This is because when your machine starts, so when you are accelerating it, you need some time for accelerating. So immediately you cannot attain your desired speed. You need some time for accelerating and to reach the particular desired speed. That 60 meter is for acceleration. So this initial 60 meter, it is going to be at reduced speed only. The initial phase will be in reduced speed. So you can take it as approximately 50% of speed of this particular segment. You can take this speed of 60 meter as 50% of the speed of the 440 meter. So initially you need some time for accelerating. So that particular distance is 60 meter, and this 60 meter the speed will be at reduced speed, and we have taken it as 50%. And similarly towards the end also, you can see that out of 400 meter, the last 60 meter you have to slow down your machine. So the time is needed for slowing down or decelerating. So that distance is 60 meter, and this distance 60 meter will be also at reduced speed. So this we can take it as 50% of the speed of this segment, 340 meter. Okay, 50% of the speed of 340 meter. So let me summarize what is given in this question. The initial 60 meter distance is for accelerating. Then 440 meter you have the 5% gradient. 300 meter you have 3% gradient. 340 meter it is your down slope minus 3% gradient, and the last 60 meter is for reducing your speed, deceleration. So, the details about your hall route is given, distance as well as the gradient percent, and you know the rolling resistance is already given to you. Okay, it will be given in the, it is given here. Assume your rolling resistance of 50 kg per ton, 5% for the hall surface. So, the rolling resistance is uniform throughout, only the gradient is varying in the hall route. Okay, that you have to note it. Then the hourly ownership and the operating cost of the machine, okay, it is given directly to you. You know very well how to estimate the ownership cost and operating cost. So, we are not going to estimate the cost again, it is given as the input data. The scraper with the operator cost is rupees 4,500 per hour, and for the push tractor with the operator, the cost is given as rupees 5,600 per hour. Now, you are going to analyze and find the probable scraper production and also find the cost to move a bank meter cube of material. So, you have to find the unit cost of production, cost per bank meter cube. Okay, you need to find the unit cost of earth moving operation. So, let us see how to proceed with this problem. So, the first thing you have to estimate is your gross weight of the machine. So, your gross weight of the machine is nothing but your empty weight plus the weight of the load in the machine. Weight of the load in the scraper bowl. Okay. So, this is your gross weight. The empty weight is given by the manufacturer. Now, I need to find what is the weight of the load in the machine, but I know what is the volume of your heaped volume of your heaped capacity of your scraper. The heaped capacity is 23.7 loose meter cube. The maximum heap capacity of the bowl of the scraper when you heap it at a particular angle of repose, it is going to be 23.7 loose meter cube. Now, what is the load volume? You need to find it. So, we are not going to load it to the maximum capacity as given by the equipment manufacturer. I will be loading to 95% of the heap capacity. So, your load volume is nothing but, so how much I am going to load it? 95%, 0.95 of your heap capacity. Your heap capacity is 23.7 loose meter cube. So, that gives me the value as 22.52 loose meter cube. Okay, 22. This is your load volume in loose meter cube. So, hope you remember, here we have to estimate everything in bank meter cube. Your unit cost of production we have to estimate in bank meter cube, cost per bank meter cube. Okay. So, let me convert the loose meter cube into bank meter cube. Okay. So, how to convert? For that we need the help of this swell factor. The swell factor is given to you, okay, in the question for this particular material, for this dry earth. So, the swell factor is given as 0.8. Swell factor is nothing but loose dry unit weight divided by bank dry unit weight. So, now let me convert it into volume. I need it in volume. Weight divided by loose volume divided by weight by bank volume. So, 0.8 equal to bank volume by loose volume. So, now you can find your bank volume. Bank volume equal to 0.8 into loose volume. So, load volume in bank cubic meter equal to your loose volume is 22.52 loose meter cube into the swell factor is 0.8. So, now you have to increase the swell factor by 10% as we discussed earlier, because it is pusher loaded scraper. Because of the additional compaction effect in the effect on the material inside the bowl, your unit weight will increase. So, you have to increase the swell factor by 10%. So, that is why I have multiplied it by 1.1. So, now you get the answer as 19.82 bank cubic meter. Okay, the load volume in bank meter cube is 19.82. So, now let me estimate the weight of the load. Okay, weight of the load inside the bowl. Okay, after I estimate the weight of load, I have to check whether it is within the safe operating limits, that is also important. So, the weight of load inside the bowl, you know the volume in bank meter cube 19.82 bank meter cube multiplied by the unit weight of the material is given in the question. The dry earth soil have the unit weight of 1660 kg per bank cubic meter. It is given in the question. You know the material property 1660 kg per bank meter cube. So, when you multiply both, you will get the weight of load as 32,901.2 kg. So, that is what is derived here. Weight of load is 32,901.2 kg. So, let me check what is the safe operating weight of the machine as given in the question. It will be given by the manufacturer. So, the maximum rated load it can carry is 34,019.42. So, this is within the safe operating weight of the machine. Okay. Now, let me find the gross weight of the machine. Gross weight is nothing but your weight of the load plus the empty weight of the vehicle. So, weight of the load you have just determined 32,901.2 plus your empty weight of the vehicle is given in the question 43,944. When you add both, you will get the gross weight of the machine as 76,845.2 kg. So, this is how you have to determine the gross weight of the machine. So, now the next step is we have to determine what are all the resistances in the haul route. The rolling resistance is uniform throughout the haul route. It is given in the question as 50 kg per ton or equivalent gradient as 5%. So, whatever way you express, you can take it accordingly. Then the grade resistance. The grade resistance is given for different sections which we discussed just now. For the first 500 meter, it is plus 5%. For the next 300 meter, it is plus 3%. And for the next 400 meter, it is going to be the down slope minus 3%. So, you can also convert it into the kg per ton. You know the conversion factor 1% equal to 10 kg per ton. This is valid for slope less than 10%. So, you can convert the gradient also into kg per ton. Okay, 5% is equal to 50 kg per ton, 3% gradient is equal to 30 kg per ton, and minus 3% gradient is equal to minus 30 kg per ton. Now, we need to find the total resistance. So, let us prepare it in a form of table, so that it will be very convenient to analyze. So, follow this table formatting. So, we can see the different the segments distances. So, for the first 60 meter, the rolling resistance is 5. You can see that for all the segments, the rolling resistance is same. Okay, 5%, it's 5% or 50 kg per ton. Next is grade resistance. Okay, for the first 60 meter, it is plus 5%. The next 440 meter, it is plus 5%. 300 meter, it is plus 3%. Then the 340 meter, you can see it is minus 3%. And the last 60 meter, you can see it is again minus 3%. You add both rolling resistance percent plus grade resistance. You add both, you will get the total resistance in percentage. 5 plus 5, 10, 5 plus 3, 8, 5 minus 3, 2. So, like that you add both. Now, you can also express it in kg per ton. Okay, just multiply it by 10. 10 into 10, 100 kg per ton. 8 into 10, 80. 2 into 10, 20. So, you can use either one of this, but I have expressed in both. So, that was about the haul cycle. Now, it is about the return cycle. Okay, the return cycle, you have to be very careful in analyzing the haul route. Okay, you know that now the machine is moving from this end to this end. So, whatever gradient we have discussed here in the haul travel, say here if it is plus 5%, in your return travel it is going to be minus 5%. Similarly, here it is plus 3%, in return travel it is going to be minus 3%. Here this is minus 3, in return it is going to be plus 3%. So, whatever it was upslope in your haul travel, in your return travel it is going to be downslope. So, accordingly you have to choose values and then estimate it correctly. So, now let us see for the first 60 meter, here the first 60 meter, you can see the gradient is plus 3%. As I mentioned earlier, the rolling resistance is going to be same. for the entire haul route. For the next 340, obviously it is same, plus 3%. Now for the next 300 meter, you can see it is now down the slope, so it is minus 3%. For the 440 meter, it is again down the slope, so it is minus 5%. The last 60 meter, it is your time, the distance where you reduce your speed, it is again minus 5%, okay, 5%, minus 5. Now add both rolling and grade resistance, so that you can get your total resistance percentage. 5 plus 3, 8, 5 plus 3, 8, 5 minus 3, 2, 5 minus 5, 0, 5 minus 5, 0. Now you can also convert the resistance percentage into kg per ton. Multiplied by 10, 80 kg, 80 kg, 20 kg, okay, 0 and 0. So now we have determined the total resistance in percentage as well as in kg per ton, okay, for the entire haul route as well as for the return route. So in order to determine the speed of the machine, I need the help of the performance chart, okay. So now with the help of the performance chart, if you know the total resistance, okay, and if you know the gross weight of your machine, you can calculate the speed of the machine as we discussed earlier. Now I need to determine the travel speed from the performance chart. The total weight of the machine is expressed in tons. 1000 kg equal to 1 ton, okay, accordingly you have to convert it into tons. So during the haul cycle, it is in loaded condition, 76.845 ton. During return cycle, it is empty, so the empty weight of the vehicle is 43.94 tons. So you have already calculated your total resistance already in both percentage as well as in kg per ton. We have already determined in the earlier slide. Now using the performance chart, okay, hope you remember the performance chart. Either I can use the total resistance percentage, or I can use the rim pull value. So hope you remember, in the left hand side you have in the performance chart, in the left hand side you have the rim pull, and in the right hand side you have the total resistance in the percentage. In the x axis you have the speed. So based upon your different gear curves, we have discussed this already. We have to, based upon your total resistance, you have to find the speed of the machine from the performance chart. So this rim pull in kg, see already we have determined earlier for kg per ton. So according to the weight of your machine, so here the gross weight of the machine is 76.845 ton. So multiply the rim pull and kg per ton into the gross weight of the machine, you will get the rim pull in total rim pull in kg. So 100 into 76.845 gives you 7684.5. Similarly, 80 into 76.845 gives you 6147.6 kg. So this 80 kg per ton is converted into 6147.6. Similarly, 20 kg per ton multiplied by the gross weight of the machine, 76.845, it gives you 1536.9, okay, 1536.9 kg, total rim pull in kg. So you can do the conversion. So you use this total rim pull or total resistance, either of this you can use, and find the corresponding speed in the performance chart. So I have assumed some approximate values. Actually you are supposed to choose the look for the correct scraper model number, okay, take the equipment handbook. In the equipment handbook, look for the particular model number, you will have the performance chart for the model number. Then from that performance chart, you know the total rim pull, corresponding speed you can find it, or with the help of total resistance percentage, corresponding speed you can find it. Similarly for your return cycle, the rim pull weight is given, kg per ton already we have determined, convert based upon the empty weight of the machine 43.94, you find the total rim pull, okay. So it is nothing but 43.94 multiplied by 80, 43.94 multiplied by 80 gives you 3515.2 kg. Similarly, say here 20 kg per ton. So 20 multiplied by the empty weight of the machine is 43.94 tons. So that gives you the value as 878.8 kg. This is your total rim pull. Okay. So you can use your either the total rim pull value or the total resistance percentage and find the speed. So one thing you can note here is your return speed is higher when compared to the Hall speed, because this is in loaded condition, return speed is in empty condition. So the speed is obviously higher. So another important thing you have to note it here is, say the 60 meter initial segment for acceleration, I have taken it approximately as 50% of 13. Okay, 50% of 13. It gives me the speed for the initial portion of the segment, where you need some time for accelerating. That portion will be at the reduced speed only. Similarly, towards again the last 60 meter, when you try to reduce the speed, so that will be also at, you have to take it as 50% of the previous one, that is 51. Okay, 50% of 51, approximately 26. Similarly, for your return travel, this is the initial segment, take it as 50%. The 14, your 14 is nothing but 50% of your 28. Similarly, the last segment, okay, 27, you take it as 50% of your the previous one, 53. So that will give you 27 approximately. So for acceleration and deceleration, reduced speed is taken, which is almost 50% of the segment. We have discussed the reason already earlier. Okay, so now you need to calculate the travel time. So we have calculated the speed. You know the speed for different segments. You know the haul distance for different segments. Now you can calculate the travel time. Okay, so time is nothing but your distance by speed. So for every segment you are going to calculate it. Say for the first 60 meter, the speed is given in kilometers per hour, 7 kilometer per hour. Haul distance is in meter. So let me convert the kilometer per hour into meter per minute. 1 kilometer per hour equal to 16.67 meter per minute, the conversion factor. So multiplied by 16.67. So you will get the answer as 0.51 minute. Okay, this is your 0.51 minute. Your travel time is segment distance divided by travel speed, kilometer per hour, into 16.67, that is your conversion factor. Similarly, you do it for all the segments. Do it for all the segments one by one. Say for the next segment 440 meter, the distance is 440 divided by distance is 440, speed is 13, the conversion factor is 16.67. Okay, this gives me the answer as 2.03 minute. The next segment is 300 meter, the distance is 300, speed is 17, the conversion factor is 16.67, that gives you the answer as 1.06 minute. Similarly, you can do it for everything. The same way for the return time. So return time, you can see for the first segment it is 60 meter, okay, divided by the speed is 14 kilometer per hour into the conversion factor is 16.67, that gives you the time as 0.26 minute. Similarly, say 440 meter, 440 divided by the speed is 53, the conversion factor is 16.67, you get the time as 0.5 minute. So add all the time for the haul route, haul time as well as the return time. If you add everything, you will get the total travel time as 6.1 minute. So this is how you have to determine the total travel time. Okay, let me now summarize whatever we have discussed so far. The travel time we have determined is 6.1 minute. Hope you remember, the travel time is 6.1 minute. Loading time is 0.8 minute, dump time 0.37, turning time 0.21, turning time in cut area 0.3 minute. So these are all your fixed time. Okay, this is your variable time. Okay, add everything, you will get the total scraper cycle time is 7.6 0.78 minutes. You have to add everything. Okay, you have to add everything. Now find the pusher cycle time. So pusher cycle time, I am going to follow backtrack loading method. So let me use the Caterpillar formula. Okay, that is nothing but Tp equal to 1.4 LT plus 0.25. Your loading time, you know already, it is 0.8 minute. It is 0.8 minute. So your pusher cycle time is 1.4 into 0.8 plus 0.25. So that gives you the answer as 1.37 minute. So we have estimated the scraper cycle time and the pusher cycle time. The next thing is we have to balance the number of scrapers and the pushers. Like say, as I mentioned earlier, we need to balance the interdependent machines so that one need not wait for the other. So by this we can reduce the waiting time of the machine. So that way you can reduce the cycle time of the production, okay, and you can increase the productivity and reduce the production cost. Okay, so that is why we have to go for balanced number of scrapers and pusher so that we can minimize the waiting time of the machines. Okay, so as we discussed earlier, you know that the pusher cycle time, it's going to be relatively smaller than the scraper cycle time. This is because your pusher will be helping the scraper only during the loading phase. Once the scraper bowl is completely filled, okay, so now the scraper will get detached from the pusher and it can haul the material on its own. Okay, so scraper need the assistance of the pusher only during its loading phase. That is why one pusher can serve even up to 4 to 5 scrapers. Okay, now let us see the balanced number of scrapers which are served by one pusher. So that is equal to n is nothing but number of scrapers served by one pusher. It is equal to cycle time of the scraper by cycle time of the pusher. So here we have estimated the cycle time of the scraper as 7.78 minute and the pusher cycle time is 1.37 minute. So it is 7.78 divided by 1.37. 7.78 divided by 1.37 gives you the value as 5.68. So now the balanced number is 5.68. This balanced number indicates a level at which the production level of both the machines are same, scraper and the pusher. So it means both are working at their maximum production level. Okay, but it is not possible for us to go by 5.68 per pusher. So we have to round it. Since we get the decimal number, we have to either round it to the lower number or round it to the higher number. Either I can go for 5 or I can go for 6. So we have to work out the economics of both the cases. If I go for 5 scrapers, what will be the associated productivity and the unit production cost? If I go for 6 scrapers, what will be the production and the unit production cost? We have to work out the economics and take a call whether to go for 5 scrapers or 6 scrapers accordingly. Now let us consider the economics of going for 5 scrapers. So 5 in the sense you are going to use lesser than what is needed. Okay, you are assuming 5. That means you are going to use the number of scrapers lesser than what is needed. Okay, so when the number of scrapers are lesser than the balanced number, okay, so obviously scrapers are more critical. Okay, but your pushers will have the idle time. Okay, your pusher will wait for the scraper. Okay, so unless the scraper is available, you cannot complete the job. Okay, so here the scraper will be controlling the production as the scrapers are lesser in number, but the pusher will have the idle time. So now let us see the productivity in this case of n equal to 5 scrapers. How to estimate the production of the scraper? The volume of your bowl, okay, volume per load, you know the value already, 19.82 bank cubic meter. We need the unit production cost in terms of the cost per bank meter cube. That is why we have to estimate the production also in the bank cubic meter. So it is already estimated earlier, the volume per load, that is the volume of the bowl is 19.82 bank cubic meter, okay, the payload in the bowl. Now the number of scrapers is 5. In this case we have taken it as 5. The cycle time of the scraper is 7.78 minute and the job efficiency, the machine is going to go for 50 minutes in an hour. Okay, now you just multiply it, so and you will find it. So basically the volume per load is 19.82 multiplied by number of scrapers is 5. So divided by the scraper cycle time is 7.78 minute. So I need the production in bank cubic meter per hour. So, let me convert this cycle time into hour divided by 60. Then the job efficiency, machine is going to work for 50 minutes an hour. So, 50 divided by 60. So, these two things gets cancelled. So, the resultant value will be 636.89 bank cubic meter per hour. So, this is your production if you go for 5 number of scrapers per pusher. Similarly, let us estimate for 6 number of scrapers. If n is greater than the balanced number, that means you are going to use more number of scrapers than what is indicated by the balanced number. In this case, scrapers will have the idle time. Scrapers are not critical. Okay, so the scraper will be waiting for the pusher. Okay, pusher is critical here. Okay, so unless the pusher is available, I cannot complete the job. Okay, so in this case, pusher will be controlling the production. Pusher cycle time is critical. So unless the pusher is available, I cannot complete my job. I have scrapers more than what is needed. So in this case, how to estimate the production? Production is pusher controlling. So the volume per load is 19.82 bank cubic meter divided by the cycle time of the pusher. Cycle time of pusher is 1.37 minute. Okay, convert it into hours divided by 60. Now multiply by the job efficiency, machine is working for 50 minutes an hour. Let's cancel. So your the production will be 723.36 bank cubic meter per hour. So that's what is given here. So basically, when we use lesser number of the scrapers, scraper will be controlling the production lesser than the balanced number. When you are using more number of scrapers, in that case pusher will be critical. Pusher the cycle time will control the production. So that is how you have to estimate the production of the teamwork. So now we have estimated the productivity. Based on productivity, if I select, okay, obviously I have to go for 6 number of scrapers per pusher. Okay, because 5 scrapers is giving you 636.89, 6 scrapers is giving you 723.36 bank cubic meter per hour. So obviously 6 scrapers per pusher is giving you higher productivity. See, if you are more concerned about the productivity, if you have a very tight deadline, you have to finish the project faster. In that case, people prefer to go for the combination which gives you higher productivity. But very often we see that people are more concerned about the cost only. So people prefer for the combination which gives them minimum production cost. Okay, so that is why now let us compare the unit production cost associated with both the cases, and then let us make the decision. Let us now estimate the cost. How to calculate the unit production cost? Okay, so cost per bank meter cube. So it is nothing but your hourly cost by hourly productivity. Now how to estimate the hourly cost? Okay, already it is given to use input data in this question, but you know very well how to estimate the ownership cost and the operating cost of the machine, which we have discussed in the earlier lectures. So in this problem, it is given to you that the hourly cost of the pusher is rupees 5,600 per hour, hourly cost of the scraper is 4,500 per hour. So including the operator cost, it is given to you. So now let us estimate the cost per bank cubic meter for the case of 5 scrapers and 1 pusher. So the pusher cost is given as 5,600 per hour, scraper cost is 4,500 for 1 scraper. So we are going to use 5 scrapers, so multiply it by 5 divided by the hourly productivity for this combination is 636.89, that is 5 scrapers and 1 pusher. The productivity value is 636.89. Now the answer will be rupees 44.12 per bank meter cube or bank cubic meter. Now let us estimate the unit production cost associated with 6 scrapers and 1 pusher. So the cost of 1 pusher is 5,600, the cost of 6 scrapers 4,500 multiplied by 6 divided by your productivity of this combination is 723.36 okay, bank cubic meter per hour. So this gives you the cost as rupees 45.07 per bank meter cube. So if you are concerned more about your production cost only, in that case. Most of the cases people are concerned only about minimizing the production cost. So, in that case we have to go for the combination which gives you the minimum unit production cost. So, the combination of 5 scrapers and 1 pusher gives you the minimum unit production cost. So, let us go by this 44.12. Okay, the solution is we are going for 5 scrapers and 1 pusher. Okay, the associated production value is 636.89 bank cubic meter per hour, and the unit production cost associated is rupees 44.12 per bank cubic meter. So, this is how we have to estimate the productivity and the unit production cost for the pusher loaded scrapers. Okay. So, we need to balance the number, and for the balance combination, for the optimum combination we have to estimate the cost. Now, so let us work out the next problem on scraper. So, in this problem we are going to check whether the rim pull generated is sufficient for doing the desired job. Okay, whether the rim pull is sufficient. I hope you remember what is rim pull. The usable force or the tractive force at the point of contact between the wheel and the ground. Okay, whether the force generated is sufficient to do the required job or not, we need to check in this problem. So, here a wheel type scraper is given with rubber tires having struck capacity of 16 meter cube and heap capacity of 24 meter cube. Okay. So, hope you know the difference between struck capacity and heap capacity. So, we are interested in heap capacity only. Okay. The machine is operated on a firm sand for which the corresponding coefficient of traction is 0.7. Okay. And the rolling resistance offered is 2%. Okay. It is expressed as a percentage of gross weight of the machine. Okay. The gross weight is nothing but your self weight of the machine plus the weight of the load in the machine, the payload, okay, in the machine. The altitude is 600 meter and the gradient is 4%, and the operating temperature is standard temperature. Okay, so that means you need not do any correction for temperature, but the machine is working at an altitude of 600 meter, so this necessitates some correction with respect to altitude. Okay, and the gradient is 4%. The rated power of the engine is 500 horsepower, and the gross weight is 76,000 kg, which includes the self weight of 42,000 kg and payload weight of 34,000 kg. The weight distribution of the scraper when loaded is 50% on the drive wheels. So, only 50% of weight is on the drive wheels. Okay? And take the efficiency for transmission to be 80%. That means the machine is the efficiency in transferring the engine power to the usable rim pull is 80%. Okay. So, the efficiency in transferring the machine power, okay, the engine power into the usable power is 80%. Determine whether sufficient rim pull is available, okay, for different the travelling speeds. Okay, different gears you can see. First gear 6 km per hour, second gear 14 km per hour, third gear 21 km per hour, and the top gear 36 km per hour. For these different gears, whether the rim pull is sufficient to do the necessary job, okay, that is what we are going to find it. So, first what we need to determine is the maximum usable rim pull. As we discussed earlier, okay, the rim pull, the maximum usable rim pull for any machine, okay, so depends upon the coefficient of traction between the wheel and the haul route, wheel and the surface. Okay. So, irrespective of whatever may be the horsepower capacity of the machine, okay, so the usable rim power depends upon the coefficient of traction. Okay. So, your horsepower capacity of the machine may be very high, but if the coefficient of traction is insufficient, okay, in that case most of your the engine power will not be converted into usable power. Okay. So, how much amount of engine power will be converted into usable power depends upon the coefficient of traction. Okay. So, between your wheel and the surface. Okay. That is why sufficient traction is needed for the conversion of most of your engine power into usable power. If there is no sufficient traction, there will be slippage of wheels. Okay. So, in that case conversion will be poor. Okay. So, that thing you should always keep in mind. So, the usable rim power depends upon the coefficient of traction and the weight on the powered running gear. That means, in your machine all the axles need not be powered, only some axles may be powered, okay, and those corresponding wheels only will be driving wheels. Okay. So, we are concerned only on the weight on the driving wheels for the usable power generation. Okay. So, that is why we take the weight on the powered running gear. So, the coefficient of traction in this problem is 0.7 and the weight on the powered running gear is given as 50%. It is given in the question as the weight distribution when loaded is 50% on the drive wheels and the gross weight, you know, it is 76,000 kg. So, 50% of 76,000 kg. So, that gives me the weight on the driving wheels as 38,000 kg. Okay, that is what is taken here. So, 0.7 into 38,000 kg gives you the maximum usable rim pull, 26,600 kg. Even if the rim pull based upon the horsepower of the machine is going to be greater than this, say for example, if the horsepower generated rim pull is going to be greater than this, okay, in that case you have to go by this value only, because only this will be the maximum limit. So, the coefficient of traction only will decide the maximum usable rim pull. So, now let us estimate the maximum power from the engine, okay, based upon the horsepower of the machine. Hope you remember this formula which we have discussed in the earlier lectures. It is nothing but the rim pull equal to 273.6 into horsepower into the efficiency in transferring the horsepower into the usable power. Here it is given as 80% in this problem, and the speed which depends upon the gear. So, the supplied rim pull in the first gear equal to 273.6 multiplied by horsepower is 500, efficiency is 80% and the speed in the first gear is given as 6 km per hour. Hope you remember the speeds are given here as the input data. So, the supplied rim pull is 18,240 kg. Now, the supplied rim pull in the second gear is 273.6 into 500 horsepower into 0.8 divided by the speed in the second gear is 14 km per hour. Similarly, speed in the third gear is 21 km per hour. Speed in the top gear is 36 km per hour. So, correspondingly, you can find the supplied rim pull in all the gears. So, one thing you should note that the maximum usable rim pull based on the coefficient of traction is 26,600 kg. Your usable rim pull, okay, the maximum the power from the engine is 18,240 kg in first gear. So, this is less than the rim pull determined based on the coefficient of traction. So, in this case obviously slippage of machine won't occur, okay. So, because there is sufficient traction, okay, and your usable rim pull will be this one. So, you have to compare this value with this value, okay, with the usable rim pull based on coefficient of traction. So, in this case, since the rim pull from the engine is lesser, we will go by this value only. Now, the horsepower rating is determined based on the at standard conditions, standard temperature and pressure, okay, as we discussed earlier, okay. Variation in temperature and the pressure will affect the efficiency of your machine, because all the horsepower rating done by the standard organization is at standard conditions of temperature and pressure. In this case, in the problem it is given that the machine is working at a higher altitude, say it is working at 600 meter. So, with increase in altitude, as you very well know, okay, the density of air will reduce. So, the ratio of fuel to air which is needed for the combustion will get affected, okay. For the internal combustion engine machines, okay, the combustion process should be efficient. For that we need to maintain the fuel to air ratio, okay. So, with at higher altitude, this efficiency gets, this ratio of fuel to air ratio gets affected. That is why for naturally aspirated machines, okay, the efficiency of the machine will be lesser at higher altitude. We have to take it into account when you detect the rim pull, okay. So, it is given by the manufacturer that for 0 to 300 meter altitude there is no loss in performance. So, beyond 300 meter altitude, for every 300 meter there will be 3% reduction in the rim pull. So, the available rim pull reduces by 3%. So, in our case the project site is at 600 meter altitude. So, for the first 300 meter no loss. So, for the next 300 meter we are going to detect it by 3%, 3% reduction in the available rim pull we are supposed to do, okay. So, that is what is done here. This is your supplied rim pull, okay, for different gears, and the deduction for 3%. You calculate 3% of the available rim pull, 18,240. This gives you the value as 547.2 kg. So, this much I have to deduct it from 18,240 minus 547.2. Okay. So, this gives me the value as 17,692.8 kg. So, this is my available rim pull after doing the altitude correction, okay, for the first gear. Similarly, do it for the second gear. Second gear, it is going to be 3% of 7,817.14 kg. This gives me the value as 234.51 kg. Now, you are going to subtract this from this 7,817.14 minus 234.51 kg. This gives me the value as 7,582.63 kg. So, I have deducted the rim pull according to the altitude. Okay. So, this is the available rim pull for the second gear after the altitude correction. Similarly, do it for the third gear and the top gear. So, one thing to be noted is the supplied rim pull is 17,692.8 kg is lesser than the usable rim pull derived based upon the coefficient of traction. So, based on coefficient of traction, we have found that the maximum usable rim pull is 26,600 kg. So, based upon the rim pull based on the engine power, so we have found that it is 17,692. So, this is less than this. So, now the actual available rim pull is going to be 17,692.8 kg. The usable is 17,692.8 kg, and there won't be slippage of the wheel. So, because it is lesser than 26,600 kg, there is sufficient coefficient of traction. Now, we have determined the available rim pull based upon the horsepower of the engine, okay, given by the manufacturer, okay, and after that based upon the project site location, that is the altitude, we have done the altitude correction, and after doing the altitude correction, what is the available rim pull we have determined. Now, we are going to find what is the available rim pull, okay, after correcting for the underfoot conditions in the project site. Okay. So, as we discussed earlier, we need some rim pull to overcome the resistances in the project site, rolling resistance and the grade resistance. Okay. So, what is the required rim pull to overcome the grade and the rolling resistance? That is what we are going to see now. The rolling resistance for the firm sand is given as 2% of the gross weight of the machine. So, the supplied rim pull required to overcome the rolling resistance is 2%, 2 by 100 into the total weight of the machine, gross weight, self weight plus the payload, that is nothing but 76,000 kg given in the question. So, 2 by 100 rolling resistance is 2% of the gross weight, 2 by 100 into 76,000 gives you 1520 kg. So, this much power is needed to overcome the rolling resistance. Similarly, the gradient is given as 4%. So, how much power is needed to overcome the grade resistance? 4 by 100 into the gross weight of the machine, 76,000 kg. That gives me the value as 3040 kg. This much power is needed to overcome the grade resistance. So, what is the total supplied rim pull required to overcome the resistances? 1520 plus 3040 gives you 4560 kg. This is the total power needed to overcome the resistances in the project site. As we discussed earlier, what is the power available for towing the load? Okay. So, that we can know only after determining the required power for overcoming the resistance. Okay. So, from the available power generated based on engine, okay, we have to deduct the required power needed to overcome the grade and the rolling resistance. Only the remaining power will be available for towing or pulling your load. So, the rim pull available for towing the load is the maximum rim pull from the engine after the altitude deduction minus the rim pull required to overcome the rolling resistance and the grade resistance. For the first gear, so after the altitude correction, the available rim pull is 17,692.8. Hope you remember 17,692.8 minus the rim pull needed to overcome the rolling and the grade resistance is 4,560 kg. 4,560 kg. So you deduct this, you will get the what is the power available for pulling the load or towing the load at this first gear. Similarly, for the second gear, you know what is the available rim pull after the altitude, say after the altitude deduction, this is the power available for the second gear, 7,582.63. So the power needed to overcome the rolling and grade resistance is 4,560. This is the remaining power available for pulling the load in second gear. Similarly, for the third gear, 5,055.09 is the power available from the engine minus 4,560 gives you the remaining power available for pulling the load at third gear. Top gear, you can see the power available is minimum, 2,948.8 kg. So one thing to be noted is in the top gear, the power available, the power generated by the engine is lesser than the power needed for overcoming the resistances, rolling and the grade resistance. That is why we cannot use the top gear when you climb the grade. So top gear can be used when there is no gradient, but when you are climbing up the grade, you cannot use the top gear. Okay, that is what we have found out in this problem. The rim pull is not sufficient in the top gear when you climb up the gradient, okay, because the rim pull available is lesser than the rim pull needed to overcome the grade and the rolling resistance. But you can use it, use the top gear when you are not climbing the gradient. But in this project it is given we have to climb the 5%. Hope you remember the gradient percentage is given, gradient percentage is say 4%. So we have to climb the gradient of 4%. So in this case we cannot use the top gear when you climb up the grade. So scraper will generate the sufficient rim pull at the third gear. Okay, first gear it is sufficient, third gear it is sufficient, the second gear it is sufficient. So the maximum speed possible will be 21 km per hour, that is in the third gear. So the maximum speed possible is 21 km per hour. Top gear may be used only when there is no gradient, in places where there is no gradient. So the conclusion is the rim pull is sufficient, okay, for the different gears, first gear, second gear and third gear. Only for the top gear it is not sufficient. Now let us see some basic guidelines how to enhance the productivity of the scraper. Okay, so basically the scraper will give you maximum productivity when the soil is in loosened condition. Okay, so that is why it is always advisable if you are going to handle a very hard terrain like clay, hardened clay. In that case, you have to go for a bulldozer with a ripper attachment, rip it first, loosen it, then use a scraper. Thereby you can enhance the productivity of the scraper. Ripping tight soil prior to loading by the scraper. Then if you go for loading in a larger pit, okay, that will also enhance the productivity. It can reduce the congestion also and waiting time. Then we can load it downgrade. Okay, when there is a option to use a downgrade for loading, it is preferable to go for downgrade loading as it will reduce the cycle time, okay, and increase the productivity. Try to keep the rolling resistance of the haul route as low as possible. How to do that? You have to maintain the haul route. Put some efforts for maintaining the haul route using a grader or a bulldozer to avoid deep pits, okay, deep ruts, so that it will reduce the rolling resistance and reduce your the cycle time and also extend the lifetime of your machine. Select the pusher, because conventionally what we use is pusher loaded scraper. So always choose a pusher size compatible with the size of scraper. It should match. So we have come to the end of this lecture. Let me summarize what we have learned so far. So we discussed how to estimate the productivity of the scraper. So we need to determine the scraper loading time first. Okay, the optimum loading time from the load growth curve. You can get it from the manufacturer. Based on the loading time, you can find the volume of the load. Then if you know the haul route data, that is your distance, okay, and the rolling resistance and the grade resistance in different sections of your haul route, then you can find the haul time and the return time, okay. Then you need to find the dumping time and the turning time. So, all these things will help you to calculate the scraper cycle time. So, then you have to calculate the pusher cycle time based upon the loading method which we are going to follow. We have discussed about different loading methods, backtrack loading, okay, chain loading, shuttle loading. So, according to that you have to find the cycle time of the scraper and the cycle time of the pusher. Now, you balance the number of the scrapers and the pusher, so that there is minimum waiting time and the production will be maximum. So, and also you should always keep in mind that the amount of energy, amount of the engine power that can be converted into the usable power depends upon the coefficient of traction between the wheel and the ground. Only if there is sufficient traction, most of the engine power will be converted into usable power. Okay. So, the total energy of engine for pulling can be converted into tractive effort only if sufficient traction is available between the driving wheels and the haul route surface. And we have worked out a problem to estimate whether the rim pull is sufficient for the particular scraper for doing the desired job. So, with this I will conclude this lecture. These are the references which I have referred for this lecture. So, we shall meet in the next lecture. The next lecture we will be discussing about the front end loaders. Okay. So, what are all the different attachments for the loaders and how to estimate the productivity of the loaders. So, we will be discussing that in detail. Thank you.